This is MEI Statistics Minor, Discrete Random Variables 1, Mean and Expectation. This is our final video, 1.5, Linear Combinations of Random Variables. If x and y are two random variables, then x plus y is a brand new random variable. It's formed by considering all the combinations of a value of x, selected at random, added to a value selected from y at random. As we would expect, the expected value of x plus y is the expected value of x plus the expected value of y. If we combine this with the result we found in the previous video, we can calculate the expected value of x minus y, because the expected value of x minus y is the expected value of x plus minus 1 times y. So using this result up here, that is the expected value of x plus the expected value of minus 1 y, which using this result is equal to the expected value of x plus minus 1 lots of the expected value of y, which again, as we would expect, is the expected value of x minus the expected value of y. Similarly, if we add a multiplication to that, we are going to get a times the expected value of x plus b times the expected value of y. And there they are, summed up. If we put a minus in the bottom one, we will also get a minus on the right hand side. We can then expand that to beyond. So if you have a third random variable, the expected value of x plus y plus w is the expected value of x plus the expected value of y plus the expected value of w. And similarly, if we add some multiplicative constants. Now it's very important that we tell the difference between x plus x and 2x. They might seem exactly the same, but in actual fact, if we let x be the score on a fair die, x plus x is going to be the sum of two random variables that are distributed according to x. So, for example, the sum of scores on two fair dice, or one fair die thrown twice. Whereas 2x is one random variable x doubled. So, for instance, the score on one fair die multiplied by 2. So you can see those are two different things. So, for example, up here, we could have that x plus x equals 3. That would be fine. But here, 2x equals 3. That's not going to work because we can't have x equal to 1.5. So to avoid this confusion, whenever we have different instances of the same random variable, we label them with a subscript. So this is one instance of the random variable x. This is a second instance of the random variable x. That stops us getting confused between the two. Okay, so we can have x1 plus x2, or even a third one, x3. We can similarly have 2x1 plus 3x2. So if we were dealing with dice, that would mean that we would double the score on the first dice, and we would treble the score on the second dice, and then add the two together. So, using this result, we can get that the expected value of the sum of two instances of x is the expected value of x1 plus the expected value of x2. However, since they are both distributed the same, that's the expected value of x plus the expected value of x, which is twice the expected value of x. Now, for equivalent results about the variance, we need an additional condition. So, if x and y are independent random variables, what do we mean by independent in this case? Well, y is said to be dependent on x if the outcome of x affects the probability distribution of y. Two random variables are independent if the outcome of one variable does not affect the probability distribution of the other, and vice versa. So if this holds, then the variance of x plus y is the variance of x plus the variance of y. However, we need to be a bit careful how we extend this, because that is going to be equal to the variance of x plus minus 1 y, which, using that above result, is going to be the variance of x plus the variance of minus 1 y. And using the result from the last slide, this is going to be minus 1 squared times the variance of y, because minus 1 in this case is simply a constant that we're multiplying by y. And once we get that, our minus 1 squared turns into a positive, and so our variance will become added. An extension to that is that if we add an a and a b on, then we're going to get a squared times the variance of x plus b squared, and it doesn't matter whether we have a plus or minus, we are always going to end up with a plus here. Now, an extension of this is that the variance of 2x from the last video, we remember that is equal to 2 squared times the variance of x, which is 4 times the variance of x. Whereas the variance of x1 plus x2 is simply going to be the variance of x1 plus the variance of x2 using the above result. Since they are distributed exactly the same, they're both going to be equal to the variance of x, and so this is going to be twice the variance of x. A good example to demonstrate this with is if x is a single die. So 2x could take any of the values 2, 4, 6, 8, 10 or 12, and they're all equally likely. Whereas x1 plus x2, that is the sum of 2 dice, so that can take 2, 3, 4, up through 6, 7, 8, and up to 11, 12. Now, the key is the data in this second set, these are by far the most likely. They are also where the mean is located, which means that the most likely values are quite close. They're quite pulled in towards where that mean is, and these outside values are quite unlikely. Whereas in the 2x case, these are equally likely to the ones close to the mean, which means that the data is a lot more spread out, and that is why the variance is so much bigger. In fact, twice as big. So don't forget that the variance of nx is n squared times the variance of x, whereas the variance of the sum of instances of x, x1 up to xn, is n times the variance of x. So that's the final video for discrete random variables 1, mean and expectation.